All right, Faraday's, we're going to look at Faraday's law and specifically a sample problem. This one's going to be taken from page 984. We're looking at number 38. By the way, these problems here, numbers 36 through 41, these problems pretty much exhaust exhaust what you should know as far as how to use the Faraday's law equation stated in the integral form. So remember that Faraday's law, it is really that the EMF is equal to minus n number of loops times d phi dt, where this is the magnetic flux, the rate of change of the magnetic flux. And this equation can be turned into the electric field times dl, where you integrate over the edge of some surface. The line integral equals minus d dt, and I've lost the number of loops and doesn't show up anymore. Really what I should have is I should have n in front, so this should be minus, and then you have this n here. But anyways, this is the magnetic flux, so b dot dA, and of course it's the magnetic flux through the surface. So this s and this s, these two s's are the same. It's just that in this case you integrate through the surface, and in this case you integrate along the edge of the surface, since this is a line integral and this is it's a surface integral. So for number 38, read the problem, see if you can solve it on your own, and if you do, then come back, watch the video, make sure that your solution agrees with what I'm going to show you. And if you get stuck, then well, come back here also and figure out what your problem was. But in the meantime, number 38, it says, so we have a long solenoid, and in this specific case, let's see if I can maybe draw it in a few perspectives. But here's the solenoid. I have this loop here, and then it continues on. So here's the solenoid. Now remember, a solenoid is not a bunch of loops, if you will, that are separate, but it's just one wire. So you have a wire, you have maybe the wire comes in here, and then it loops around, and maybe it thinks this thing comes out somewhere in the back here. Right, so it's just one wire that loops around. But I'm just going to keep it like this. And then what we have here is, we have the radius, 2.5 centimeters. This is the radius of this thing. So I'm going to put here that r equals 2.5 centimeters. We don't have the length of this. We don't have the length of the solenoid, but what we do have is the density of the turns. So what we have is, let's call this thing little n, where little n is 900 turns per meter. So we have the density of the turns. We don't have the actual number of turns in the solenoid. We just know how many turns are packed per meter. And all right, and then what's given to us is the rate at which the current changes. So there's a current in this loop. Let's indicate that. We have a current in this loop, and let's say that the current flows in this direction. So here's the current I. And this current I is not constant. So the current I changes at a certain rate, constant rate. So we don't know what its value is at any point in time, but we know that it changes in a specific way. And so I'm going to write here that di dt is 36 amps per second. So every second the current I is increasing. Yeah, let's put plus here, just so that I remember that this thing is actually increasing, not decreasing. Okay, so the current is increasing. Now, if I have a current here in this loop, then what I have is well, first of all, every solenoid is going to have a magnetic field set up, and we already went over that, so you should know this. There's a magnetic field that points through the solenoid and goes like that, and when it gets to this point, it just loops around. Maybe I'll draw one more loop here. So here's a loop, and it loops around and comes back. So here's the magnetic field, and of course between these two lines you have many more lines of the magnetic field. Now we're not interested in the magnetic field on the outside of the solenoid, just the magnetic field on the inside. So I suppose what I could do is I could redraw this a little better perhaps, and then just put a few turns here, and then indicate that we are interested in the magnetic field only on the inside. And so I'll draw a couple lines here. Here's the magnetic field B. And this magnetic field B, you can look up the equation. It's just mu naught times I times N, where N is in fact the density of the turns. We derived this equation before. I think we did it 2 different ways, but here's the magnetic field on the inside of the solenoid, given current I on through this solenoid here. Now, what's happening though is that the current is not constant, and so we'll take the derivative of this expression. If you take the derivative of this expression for the magnetic field, then you end up with dB dt equals mu naught and n are constant, so this just comes out mu naught and n are constants, and you end up with di dt. So what you have here is an equation that relates the rate of change of the current I to the rate of change of the magnetic field, and of course you can take it a step farther and you can write that dB dt here is mu naught times 900 times 36, and you have an actual constant, you have an actual rate at which the magnetic field changes. The units here would be Teslas per second. All right, so let's keep this, or actually let's calculate this thing, because at some point I think we will need this. So dB dt equals, remember mu naught is 4 pi times 10 to the negative 7th. So let's calculate this thing. So this is 0.041 Teslas per second. This is the rate at which the magnetic field is changing. And in fact, this magnetic field is increasing. So plus the magnetic field B is increasing every second by 0.041 Teslas. Now, what is it exactly that we're looking for? So far all I've done is just sort of, this is what the problem is talking about. This is the picture that we have in the problem. I think I know where this is going to go. Yeah. So if you have a changing magnetic field, recall that if you have a magnetic field and magnetic field points in this direction, and then this magnetic field is changing with respect to time, then that implies that this right-hand side here is not equal to 0, right? You have the time derivative in here, and since B depends on time, then this time derivative is not 0. Therefore, the whole right-hand side here is not 0, and that means that the left-hand side is not 0 either, and so you have E dot dl. But if E dot dl is not 0, then that means that the electric field in this space is not 0 either. And so suddenly what you have is an electric field that is not 0. And the question is, what is this electric field? So if the magnetic field here is changing, you're going to end up with some electric field in a space around this thing. So maybe I'll draw kind of an electric field, and I'm drawing it in a circular fashion here. Like this, to indicate something, but I think I'm just going to get rid of it, to be honest. Instead, let's just look at that's interesting. Let me see if I can, oh, okay. So let's look at the loop here. What I have is, well, actually, let me redraw it like this. I think maybe let's say that this is your face, and you're looking at this loop here from this perspective. So there you are. Let's give you an ear, an eye, some hair, and you're looking at this solenoid. You're looking into the solenoid, so that this is your perspective looking into the solenoid. So here's the loop, right? The current flows in this direction, I. And the magnetic field comes out of the page, comes at your face. Magnetic field is coming at your face, and so you have a bunch of dots here. I'm going to put a bunch of dots for the magnetic field B. And this magnetic field is increasing as it comes at you out of the solenoid. So what we want to find out is because there's a changing magnetic field, so I'm going to put here magnetic field is changing with time, there's going to be an electric field present in the space, and I already went over that reasoning. It's just this long equation here, and the electric field is going to point, you don't know how to determine the direction of the electric field yet, but that's okay, as long as you can calculate the magnitude of the electric field, and then with Lenz's law you should be able to figure out the direction. But although if you know how to play with the curl, then you might be able to get here. But anyways, let me figure out the direction of the electric field. All right, so the electric field will actually, everywhere here in this space, electric field will actually point in the direction that is opposite of the current. And in that sense, the system will oppose a change here. But so I'm going to indicate this, let's say along this line here. So here's the electric field. The electric field will point in this direction, and in this direction, and in this direction. And that electric field is going to oppose a change, going to oppose an increasing current. And this concept will actually tie us into the Lenz's law, but we're not ready for it yet. So electric field will point like that, and then if you move a little closer, electric field will still point like this. So this would be the direction of the electric field, and then if you go out here, you would have an electric field that probably would be a little bigger. Well, we still need to actually, like, we don't know that yet. Let's just go back. Let's calculate the electric field, and then we'll see how it varies with the radius r. So there's going to be a radius r from the center, and let's see how electric field varies with that r. So given everything that I have, let's go ahead and take the Faraday's law equation and let's start playing with it. So what we have is on the left hand side E dot dl over the surface S, and of course the surface S is the surface S, and on the left hand side I integrate along the edge of that surface. On the right hand side I integrate. I have loops here, right? I have a number of loops. I don't think I have to worry about it. Okay, so d dt, that's going to be taken care of by the magnetic field. So here's the integral b dot dA, and I integrate over the surface S, right? But here in this case I integrate over the area. And so the left hand side, I already told you that you can, for all of these problems here, you can assume that the electric field is just going to be parallel to dl. You can actually figure this out by using Lenz's law that I haven't mentioned yet, but and that also the electric field along a circular path is going to be constant. So electric field is constant along a circular path. And so in that sense, the left hand side simply becomes E dl, where you just integrate through the whole length of the loop there, equals, and then you have minus d dt. This just becomes b times dA. Reason being is that the magnetic field is parallel to the element dA, and so that simply means cosine 0. I end up with cosine of the angle 0, which is just 1. And b, all right, so now what happens is this, the left hand side, E times, well, the length of the loop that's just the circumference of the loop that I have there. And so this would be simply 2 pi times r, and r will be whatever I want it to be as it moves from the center towards the actual solenoid, equals, and then I have minus d dt. The expression for the magnetic field is mu naught times n times I times dA. And now mu naught is a constant, n is a constant, I is not a constant, but this I has nothing to do with dA. So I can pull all of this out of here. So what I'm going to have is E times 2 pi r equals minus d dt of mu naught times n times I, and then the integral of dA. Of course, I integrate to get the full surface. Again, I was able to pull I out of the integral simply because I is not changing in respect to the physical dimension of dA here, right? dA is dx times dy, and I does not depend on x or y. It just changes with time. And so what I have here is, let's keep going, 2 pi r equals minus mu naught times n times, I'm gonna write it this way. Do I really have to? Times I times just the area A, and that would be pi r squared. And of course, this is a constant, so I can pull this out. And so now what I'm gonna have is the electric field times 2 pi r equals minus mu naught times n times pi r squared. times, just gonna, there's no need for that partial, there's no need to have a partial derivative here, di dt. And so pi goes away, r goes away, at least that part of it. And so now what I have is that the electric field, actually, it looks to me like I might have done more work than necessary, but the electric field then equals minus mu naught times n times r over 2 times di dt, which is just 36. And so this gives me the electric field is equal to the negative. Negative is always needed there too, for the sake of the Lenz's law, but let's keep it there for the moment. So what I have is E electric field is equal to 18 mu naught times n times r. I can plug in the numbers here so that the electric field becomes, remember that n was 900. And so when I plug in the numbers, what I'm gonna get out of it is, so we get, let's keep that negative, so we get 0.02 times r. That's the expression for the electric field. It varies, it doesn't vary with time, it varies with the distance, r, from the center. And so at the center, the electric, I'm at this point here. At the center, the electric field is 0, and then as you move out, the electric field increases. And in fact, if you were to continue beyond the solenoid, so let's say you went on beyond the solenoid, the electric field here would be even bigger. And somewhere out here, the electric field would be even bigger. Somewhere out here, the electric field would be even bigger. And so let's maybe add this for completeness. Although maybe it will just make this thing more convoluted. So I'm not sure we need this, but anyway, I guess I'm doing it. So I'm doing it. So this would be the electric field set up by the changing magnetic field. And note that this electric field would oppose the flow of the charge here. And in a sense, it makes sense. Like, nature tends to oppose change. That's a very general statement. But anyways, nature tends to oppose change. And so since the current is increasing in its magnitude, somehow this system will oppose that change. And in fact, it's going to be through this electric field that the increasing current is going to be opposed. Now, the problem asks for electric field at R equals, let's see what it was. So near the center at R equals 0, and that's easy enough. That's 0. It asks for the electric field at R equals 0.5, half a centimeter. So I'm going to write here 0.5 centimeter. 0.5 centimeters. And then it's easy to calculate. I'll leave that out to you. And then the last one is find the electric field at R equals 1 centimeter from the center, from the axis of the solenoid. So at 1 centimeter, and then you plug in whatever you need to plug in for R, and you get your answers here. That should be easy enough to calculate. All right, so here's another. So this here's a sample problem using Faraday's law, the integral form, using this.